So now we're ready to start working on some variations on the graphs of the basic graphs of sine and cosine. So we're full into step 4 in our development of the trigonometric functions. And on a yellow card here, I have sketched the basic graphs of sine and cosine. Notice how for each I rely on the quadrantal angles, pi over 2, pi, etc. I have the vertical axis labeled with -1 and 1 to clearly be able to see the range, and I marked a period for each of them. Each of these functions has period 2 pi. So what's on this yellow card is something you just absolutely have to memorize. You need to know how sine and cosine are similar and yet different, and you're going to use these basic graphs of sine and cosine to draw all sorts of other graphs. So let's go ahead and get started on that now. I actually have a handout posted, a worksheet handout posted in Canvas. You can just print this out if you want. It looks like what you're looking at right now. But to work on the video, I recopied these on a separate paper. So that's what we're going to be working from as we go through these exercises. And let's go ahead and start graphing one of these, y equals 2x. Now, our goal is to be able to graph these fairly quickly, and you don't have to set up a table of values each time. I'm going to do that here since we're just getting started, but once we get the hang of it, I think we'll be able to sketch quickly without even setting up a table. So now my input is x. It's the what we were calling the theta value of an angle, right? My output here is going to be 2 sine x, not just sine x. And if I just think of my quadrantal angles, 0, pi over 2, pi, 3 pi over 2, 2 pi, that's normally going to be enough for me to figure out what's going on with the graph. So let's go ahead and plug into this function. When x is 0, y is 2 times sine of 0, which of course is 2 times 0, or 0. So we have the point 0, 0. At pi over 2, we get 2 times sine of pi over 2, which is 2 times 1. So notice the y value becomes 2 now, because we're taking 2 times 1. At sine pi, 2 times sine pi. Sine of pi is 0, so we're taking 2 times 0 again. Of course, that'll just be 0. At 3 pi over 2, 2 times sine 3 pi over 2 is 2 times a -1. So we're going to be stretched out to -2 there. 2 times sine of 2 pi is 2 times 0, which is 0. So my points here, some of the points are just going to stay right where they're at with the graph of sine, like 0, 0. But at pi over 2 now, I have to go 2 units up. At pi, I'm back at 0. At 3 pi over 2, I'm at -2. At 2 pi at 0. Now, I'm just plotting a few points, but I know what a sine wave looks like now. So I know the graph is going to be kind of stretched out away from the horizontal axis or the x-axis because of this effect. Now, there's one period of the graph. I'm normally going to ask you to draw at least 2 periods. I want you to be aware that this is not the entire graph of sine. It extends on in both directions. So by drawing 2 periods, I think it just sort of reinforces that idea that this graph continues infinitely in each direction. So I actually got half of another period here, so I'm going to go in the negative direction and extend. I know at -pi over 2, I'll be at -2. At -pi, I'm back at 0. So I know that pattern's just going to repeat over and over once I get a few points plotted. So there's 2 full periods drawn of the graph of y equals 2 sine x. I'm going to introduce a word here. The distance from the x-axis to the top of the graph is something we call amplitude. If this were a sound wave, amplitude is a measure of how loud the sound is. And here the amplitude is 2, the distance from the x-axis up to the top. And one other thing I want to do to this graph is I'm actually going to just add in red the graph of the regular sine function, which you don't normally have to do. But I just want us to be able to compare the difference between these two. So in red here, you see y equals the good old-fashioned sine x. And there's our first example of a kind of a stretching effect, right, caused by multiplying by 2. Okay, now let's look at what happens in another slightly different situation if we multiply by -2. If you can just see what's going on, you don't need to write a table again, but I'm going to write out some values here. When x is 0, we get y is -2 sine 0, which is -2 times 0, which is 0. So changing that coefficient to -2 still leaves us with the 0, 0 point, right? But at pi over 2, I get -2 sine pi over 2, which is -2 times 1, which is -2. So this is a difference from the previous graph. We've kind of flipped to a negative place. -2 sine pi is -2 times 0 is 0. And now notice that at 3 pi over 2, we'll get -2 sine 3 pi over 2. I think you can see what's going on here. -2 times -1 will be +2. So where the original graph of sine is negative, this graph is going to be positive. And at 2 pi, I'm back to -2 times 0 is 0. So if I plot these points, 0, 0, and pi over 2, -2. So I'm down here, then here, 3 pi over 2, I'm back to positive, 2 pi to 0. So this graph starts out by going descending down to this low point, turns around, and rises up. So the effect, I still have this sine wave pattern, but notice the effect of the -2 coefficient. At 5 pi over 2, I'm at -2. And at 3 pi, I would be back at 0. I don't have to evaluate. I know that's going to be the shape. And it continues. In the negative direction here, so at -pi over 2, I know the value is going to be +1. You can, of course, you can plug in and check if you want, but you shouldn't have to. So there's a graph of -2 sine x. We still say, even though we've flipped around, when we talk about the amplitude, amplitude is always positive. Amplitude is just a measure of how far the graph rises from its midline, its middle, on the x-axis. So we say it's positive. So for this example and the previous, we say amplitude is 2. The amplitude doesn't distinguish between the positive and -2. So you still have to know this has a negative coefficient affects the shape. The amplitude just doesn't tell us that that coefficient is negative. And here's, again, the graph of the regular sine function just for comparison. There's y equals sine x added to the picture, which you don't normally have to do. I'm just going to do it a couple times in this exercise. And I think I'm going to stop here. We're going to do a couple cosines in the next video.